So the present value, if you're trying to find the present value over some period of time, and you're given some income function, C of t, and some inflation rate, R, or if you're talking about like an interest-bearing account, R can represent the interest rate, then the present value is just this interval from 0 to whatever time period you're looking at of your income function times e to the negative RT. And that's kind of it. So if your income function is easy, like you're getting $50,000 per year, and your inflation rate is 4%, and your time period is 3 years, we can pretty straightforwardly calculate the present value. Here, the present value is going to be the integral from 0 to 3 of 50,000 times e to the negative 4t. That's a really straightforward calculation. The integral of e to the negative 4t is e to the negative 4t divided by negative 4. So this is going to be 50,000 e to the negative 4t divided by negative 4 from 0 to 3. 50,000 divided by 4 is what? It's 25,000 divided by 2, it's 12,500. This is negative 12,500. And then when you plug in 3, you get e to the negative 12, minus when you plug in 0, you get e to the 0. So that's going to be, let's actually get out of the calculator. Wait. Oh, excellent. That's good call, Joanna. I'm making a real bonehead mistake there. Right. So your R is your inflation rate as a decimal. So a 4% interest rate is exactly a 0.04 interest rate. Good call. Yeah. Usually I don't make that mistake. I was really just trying to make sure you guys were paying attention. So that should be a 0.04. So actually, let me finish this calculation just because I want it. Well, no, it's not really going to be super. I was going to finish and show you like we're going to get something that's really weird, which might or might not be obvious. So this should be a 0.04 t. And we're dividing by negative 0.04. So 50,000 divided by 0.04 is going to be 12,500 times another 100, right? Because, so it's really going to be 12,000 and then 2 more zeros, like that. And then we should have e to the, instead of negative 12, it'll be negative 0.12. So let's see. So if we calculate this, so I'm actually going to change this a little bit. I'm going to make this up. I'm going to make this a positive 1.25 million times. I'm going to switch the order of subtraction here. E to the 0 is 1 minus e to the negative 0.12. Okay, so let's see. E to the negative 0.12 is 0.88 approximately. 1 minus that is about 0.11, and then times 1.25 million is giving us about $141,349.45. Okay, so to think about what's happening here, right? We're making $50,000 a year for 3 years. So over the 3 years, we would make $150,000. What we're saying is that instead of making $150,000 every year for 3 years, if you started off with this amount of money, $141,349.45 right now, that amount of money would have the same purchasing power because of inflation as this $150,000 that we get over 3 years, if your inflation is 4%. So that's the whole idea. This calculation is pretty easy, assuming you don't make stupid mistakes like I did. But right, it's easy to make mistakes. But let's look at one that's a little bit more challenging. So it's really easy. It's relatively easy when your income function is just a constant. You're making the same number of dollars every year. It's a little bit more challenging when your income function changes over time. So this is actually problem, I believe 69 from your textbook. Yeah. So a company expects income to be $150,000 plus $75,000 times T, where T again is measured in years for the first 4 years. So the first year or after the first year, it's going to make 175 or 150 plus 75, so 225. And then after the second year, it's going to make 150 plus 150, which is 300. So each year they're expecting their income to increase, at least for the first 4 years. So we want to calculate both their actual income over the next 4 years and their present value. So the actual income, again, is not too hard. And actually, I want to make one. I just want to see one thing here. Oh yeah, I'm just being silly, right? The actual income. The actual income is just the integral of their income function. So the actual income they're going to get is going to be the integral from 0 to 4 of this income function, which is 150,000 plus 75,000 T. So that's going to be, let's see, you're going to get 150,000 T plus 75,000 T squared over 2. 75,000 divided by 2 is 37,500. So it's 37,500 times T squared from 0 to 4. Plug in 4, you're going to get 150,000 times 4, which is 600,000. And you're going to get 37,500 times 4 squared. Minus when you plug in 0, which will both be zeros. And let's see, 37,000 times 37,500 times 16. That's also 600,000. So you're going to get 600,000 plus 600,000, which is going to be what? $1,200,000. Okay. And let me just think for a second here. Yeah, right. So every year you're going to get $150,000, and every year you're also going to get, right after the first year, you're going to get 75, and then 150, and then 225, and then 300, right? Which should, yeah, I think, just for me, so the numbers make sense. 225. Sure. Yeah. Okay. On the other hand, right, so that's how much actual income this company expects to make over the next 4 years. But if there's a 4% inflation rate, the present value rate, so if you said, how much money would you need today to have the same purchasing power that you're going to have with this money made over the next 4 years? Well, that's going to be this calculation, the integral from 0 to 4 of e to the not 4t, but e to the negative 0.04 t times your income function, which is this 150,000 plus 75,000 t dt. All right, I forgot my dt up here. That's terrible. Okay, I'm going to erase a little because I'm kind of out of room. But we're going to have to break this integral up into 2 pieces. So I'm going to write this as the integral of 150,000 times e to the negative 0.04 t. And this should be a fairly straightforward antiderivative to do. But then we also have to do the integral from 0 to 4 of e to the negative 0.04 t times 75,000 t. Or if we pull out the 75,000, which I guess I could have done here as well, it's 150,000. 75,000 times the integral of t times e to the negative 0.04 t. Zero to 4, 0 to 4. All right, so again, I want to point out these present value problems aren't specifically challenging in that you're just throwing it all into a formula. Yeah, the integral might not be pretty, but still, at least the start of it is just like, oh, there's a formula for that, toss everything in your formula, and then do the unpretty integral. Yeah, we can remember that $1.2 million. So doing this, you're going to get 150,000 e to the negative 0.04t divided by negative 0.04 from 0 to 4. And that's going to be something. So one thing I did last time, which I want to point out again, is that right when I do this, so 100,000 divided by negative 0.04, probably just get to not screw it up these calculators. So 150,000 divided by negative 0.04 is going to be negative 3,750,000. Right. Okay. And then we've got e to the negative 0.04 times 4 minus e to the 0. And what I did last time, which I'm going to do again, is I said, well, this is something minus 1. I'm going to distribute the minus sign in there and make that 1 minus something. So I'm actually going to write this part as positive 3,750,000 times 1, right, which is that, minus e to the negative 4 times 0.04 is 0.16. That's just going to make it easier to plug things into a calculator later. Okay, so that's half of it. But then we have to do this other half. And this other half, we have to do integration by parts for, because you have an algebraic thing or a power of t times an exponential thing. So for that interval there, I'm going to let u equal t, and dv has to be the rest, the e to the negative 0.04t dt. Your du is going to be dt, and your v is going to be the antiderivative of this, which is e to the negative 0.04t divided by negative 0.04. So when you get the integral, and I'm going to write the integral down here so that I don't have to carry my limit of integration with me. I'm going to get uv, so t times e to the negative 0.04 t divided by negative 0.04, right? That's my uv minus the integral of v du, which will be, so I'm going to put the negative 0.04 out in front, the divided by, I should say. Integral of v du, so that's going to be e to the negative 0.04 t dt. Right, so this is, I mean, it's terrible, but it's not that terrible. A minus will be a plus. And so then we can write this as negative t e to the negative 0.04 t divided by 0.04 plus 1 over 0.04, and the integral of e to the negative 0.04 is e to the negative 0.04 t divided by another negative 0.04. All right, so here's what we've got. It's gross, but we've got, let me write it in a different color just so so it can be a little bit more clear what's happening here. I've got all of this. So I've got negative t e to the negative 0.04 t divided by 0.04 minus, right, because it's a positive times a negative here, e to the negative 0.04 t divided by 0.04 times another 0.04 is 0.00. How many zeros? Good question. I was never good at multiplying decimals, to be honest. 0.04, 0.04. I think you get like 4 spots, and then a 1/6. That seems reasonable. I would like to double check it though, just to be sure, because I don't want to make mistakes. Nope, totally off. Too many zeros. I don't know why. 0.0016 seems too small. No, that's right. 0.0016. Oh no, that's right. Okay, I'm sorry. My brain was just not seeing it the right way. All right. So yeah. Evaluated from 0 to 4. Yeah. So, right, not very nice, not terrible to calculate, but again, kind of gross. So you're going to get, right, this part's going to be -4 times e to the -0.16 over 0.04. Now, 4 divided by 0.04, that's 100. So let's make that a -100. And then minus, plug in 4 here, you get e to the -0.16 divided by 0.0016. And then minus, and you have to plug in the 0. That's going to be 0 because there's a t there. So 0 is just 0. And then the 0 here, you're going to get e to the 0, which is 1 over 0.0016. That's pretty gross. This definitely, to me, requires a calculator. So let's see what we've got, though. Well, I forgot the 75,000. There's a 75,000 there. So it's 75,000 times all of this. So it's 75,000 times, let's simplify a little bit. So a minus is a plus. So it's 1 divided by 0.0016 minus 100 e to the -0.16 minus e to the -0.16 divided by 0.0016. We could calculate this. I suppose we should calculate this just to see what it was. So let's see what we've got here. First of all, 1 divided by 0.0016 should be something like 625, I think. Yep, 625. Okay, so this is really 625. And this is really 625 times e to the -0.16. Before I calculate this, here's what I want to mention. The work we've done here is more than sufficient. And if you had to, so again, if you have to enter something into, I don't think I saw any homework problems on present value on anyone's homework yet. But if you had to enter something, right, you don't typically want to enter a decimal approximation. You want to enter something more exact. So you probably want to enter kind of all of this, which is terrible. Let's actually find out what it is approximately. So this, yeah, I guess I'm after approximately. So this is going to be, let's see, 1 minus e to the -0.16 times 3,750,000 is approximately $554,460. I'm going to leave off the decimal. And then this one here, so you've got 100. I'm putting these together. This is minus 725 e to the -0.16. So you've got, yeah, sure. 725 times e to the -0.16, which is 617, and then 625 minus that. Whoops. Is about 7.1, and then times 75,000 is approximately $539,681. So you add those together, you get about you get about $1,094,141. So again, what that's saying is because of inflation, if you had this much money today, it would be the equivalent of getting the $1.2 million of income over those 4 years, spaced out how the income function said it was. So this much money today has the same purchasing power as that $1.2 million over those 4 years. It's kind of a funky concept, but it does work. And definitely how lotteries work as well, right? They say, okay, you've won this much money. We're going to give you like kind of like half that much because, or you can take the lump sum or the payout. And the lump sum is, well, if you have this much money, it has the same purchasing power as what your payout would give you over the next 20 years or whatever. All right. let's move on. So I feel like we should do a few more partial fractions examples because partial fractions definitely can be a little bit challenging. I'm trying to remember, I don't remember exactly which one we did yesterday, or sorry, Tuesday. Then we can't come up with some more examples. I don't think we did this one. Sure, let's take a look at this one. So let's say we want to do the integral of 3x squared plus 1 over x cubed minus 2x squared plus x. Okay, this definitely fits into our criteria of, well, actually, I should always say, before I jump straight to partial fractions, I should usually consider, can I do a use of? If I let u equal the denominator, my du is 3x squared minus 4x plus 1. So close, right? If I had a minus 4x up there, a u sub would have totally worked out perfectly. But we don't, so it's not great. Basically, if you're doing a u sub where you let u equal the denominator, you want the du to be either exactly the numerator or a multiple of the numerator. We don't have that. So, all right, but if the numerator, for example, if you had, say, if this had been the problem, if the problem had been 6x squared minus 8x plus 2 over x cubed minus 2x squared plus x, this would be perfect for a u sub, because you let u equal the bottom, your du would be 3x squared minus 4x plus 1 dx, and then we can see, oh look, this integral is really just 2 times 3x squared minus 4x plus 1 over x cubed minus 2x squared plus x dx. So here this would totally just be the integral of 2 du over u, which would then be 2 times the natural log of the absolute value of u. And then that would be 2 times the natural log of the absolute value of x cubed minus 2x squared plus x plus c. So, long story short, if you have a fraction, if you have a rational function you're integrating, and it's meeting the criteria for partial fractions, meaning degree on top is smaller and the bottom factor is, even though it's meeting those criteria, it's still worth taking a look at, could you do a u sub? In this problem, you totally could do a u sub, and we typically think of a u sub as being an easier process. But this problem, we cannot. So we're going to do the partial fractions. We're going to say, all right, I can see that my denominator factors, I can factor out an x, and I'm left with an x squared minus 2x plus 1. And we want to factor it completely. That denominator factor is one more step. That factor is x minus 1 times x minus 1, which is x minus 1 squared. So you do not want to write it as x minus 1 times x minus 1, right? Because I don't want to say this is a over x plus b over x minus 1 plus c over x minus 1. Having the same thing there is not good. What you want to say instead is this is x times x minus 1 squared. And then we know that when we have a repeated factor, when you have a factor that's to a power that's higher than 1, you need that highest power and then every lower power. So my partial fraction decomposition here is a over x plus b over x minus 1 squared plus c over x minus 1. Hopefully you can kind of see that. Let me write it again, just so it's more easy to see. A over x plus b over x minus 1 squared plus c over x minus 1. Again, it doesn't matter if you write them in ascending or descending order. I used to write it ascending, to be perfectly honest, but I feel like it's easier to remember that if you write the highest power first, then you need all the lower powers. So I've been writing them in descending order, but again, it really, really, really doesn't matter. You could have yours as c over, right? You could have yours as a over x minus 1 plus b over x minus 1 squared plus c over x. You'll get the same answer. You'll just have slightly different names for things. Okay, so then we have to multiply both sides of our denominator. So, right, typically people kind of just jump to the next step, but I really want to make sure everyone knows that what we're doing in this step is we're multiplying everything by x times x minus 1 squared. So that's distributing to each of my terms. When you multiply this by that, the entire denominator cancels, and you get 3x squared plus 1. When you multiply that by that, the x cancels, and you get a times x minus 1 squared. When you multiply this by that term, the x minus 1 squareds cancel, and you get b times x. And when you multiply this by this, one of the x minus 1s cancel. So you get c times x minus 1. I will also remind you, when you have a repeated factor, you're always going to run out of convenient values of x. So my convenient values of x here are x equal to 0, because that makes that denominator 0, and x equal to 1, because that makes those denominators 0. So I know I'm going to use x equal to 0 and x equal to 1. So when I plug in 0, I get 3 times 0 plus 1, so I get 1. On the right side, I get a times negative 1 squared. And I get b times 0 plus c times 0. So zeros. So I end up getting 1 equals a. Great. When I plug in 1, I get 3 times 1 plus 1, which is 4. And I get a times 1 minus 1 is 0. I get b times 1. And I get c times 1 times 0. So I get b equal to 4. And now I've run out of convenience. So here's where I do what I like to call equating coefficients. So let me actually, usually I don't multiply things out. So I'm going to show you, let me show you the short way and the longer way. The short way is to say, okay, what's the highest power of x on either side? Well, the highest power of x is x to the second power. So I'm going to look, and I always start with the highest. Usually it's best to start with the highest because there's kind of the least number of terms that have the highest power. If you were to multiply this out, this would be x squared minus 2x plus 1 times a. So you would have an a times x squared. You don't have any b times x squared, but you do have a c times x squared. And on the left side, you have a 3 times x squared. And since these polynomials are equal to each other, the amount of x squared on the left has to be the same as the amount of x squared on the right. Meaning this 3x squared has to equal ax squared plus c squared, or 3 equals a plus c. And since I know a is 1, I know that c has to be 3 minus 1, which is 2. But let me show you the longer amount of work. So here's the long work that we're not going to show usually, that we're shortcutting. What you're really doing is saying, okay, I have on the left 3x squared plus 1. And on the right, if I multiply this out, I have a times x squared minus 2x plus 1. I have bx, and I have c times x squared minus x. And then I can multiply it all out. So let's see, I have an ax squared plus a cx squared. I have a minus 2ax plus bx plus, or sorry, minus cx. And I have an a, and that's the only constant term. So if you want to write this in kind of the normal polynomial way where the powers of x are descending, this would be x squared times a plus c plus x times negative 2a plus b minus c, and then plus a. And this has to equal 3x squared plus 1. So now you can actually equate all the coefficients. Say, okay, well, the constant term here is a, the constant term here is 1. So a has to equal 1. Great, we already saw that. And the coefficient here is 3. So a plus c has to equal 3. So since a is 1, c has to equal 2. And then the coefficient of x is 0. And since we know that c is equal to 2 and a is equal to 1, we know that negative 2 times 1 plus b minus 2 has to equal 0. So that b has to equal 4. So some people, not me, some people prefer to just only use equating coefficients to solve for your a, b, and c. That's too much work. It is much, much, much easier to first use any convenient values of x, meaning values of x that make things 0. And then if you've exhausted all of those, then equate coefficients to find whatever's left. Okay, now we actually have to do the integral. Let me erase. Sure, where can I erase? I guess I can erase down. I guess I can erase up here. So this is going to equal the integral of 1 over x plus 4 over x minus 1 squared plus 2 over x minus 1. Okay. The 1 over x and the 2 over x minus 1 are easy, right? Those are just logarithmic integrals. So you get natural log of the absolute value of x. We'll leave this one alone for a minute. And you get 2 times the natural log of the absolute value of x minus 1. Now this part here, well, that's really the integral of 4 times x minus 1 to the negative second. And while we could do a u sub, you don't even really have to, right? If you let u equal x minus 1, your du is dx. So if you did let u equal x minus 1, you'd have the integral of 4u to the minus 2 du. And we know how to integrate that. You just add 1 to the power, divide by the new power. So you're going to get 4 times your u to the minus 1 divided by minus 1. And I want to point out, if you've got just x plus or minus something to a power, you can really just say, well, like, I know how to anti-differentiate x to a power. It's just add 1 divided by the power. And if it's x plus or minus something, it doesn't really actually change it because your u substitution wouldn't have you multiply or divide by anything. So just to kind of make that even more clear, I really want to emphasize, here are some integrals that we should be able to do without having to do a u substitution. The integral of, say, 1 over x plus 3 to the 4th. And the integral of 1 over, let's make it 2x minus 1 to the 3rd. And let's do one more. Let's do the integral of, I don't know, 5 over 3 minus 2x to the 6th. Okay, so the one thing we might want to do is rewrite this, right? We could think of this as the integral of x plus 3 to the negative 4th. And the integral of that is just going to be x plus 3 to the negative 3rd divided by negative 3. Which you might want to rewrite. You might want to rewrite this as negative 1 over 3 times x plus 3 cubed. I don't think you need to rewrite it, but some people do rewrite it. Same idea here. I've got the integral of 2x minus 1 to the negative 3rd. And when I integrate that, I'm just using my power rule again. I get 2x minus 1 to the negative 2nd divided by negative 2. Now, there is something else I have to divide by here. Any guesses as to what? You guys should have guesses. It's the same kind of thing we've been doing a lot when you do like a mini substitution. You should also be dividing by the coefficient of x here. And because the derivative of this, right, if you took the derivative of this power to that, you get negative 2 times your stuff to the negative 3rd power, but then you have to multiply by the derivative of your stuff. The negative 2 that came down cancels that negative 2, and the derivative of 2x minus 1 is 2, which cancels that 2 there. Same idea here. This is going to be the integral of 5 times 3 minus 2x to the negative 6 dx. You're going to get 5 times 3 minus 2x to the negative 5th divided by not only negative 5, but also this negative 2 that's a coefficient of x. And then, yeah, you can simplify that. Again, I'm not too worried about simplifying it. But what I really want to emphasize, right, you're going to see integrals like this, and you want to just be able to anti-differentiate them without having to be okay. Like you could totally have said here, all right, we're going to let u equal 3 minus 2x, and then du is negative 2 dx. This pen is really bad. And then negative 1/2 du equals dx. So then you could have written this as the integral of, negative 1/2 5 over u to the 6th du. And then, right, it's negative 1/2 integral of 5 u to the negative 6 du. You get negative 1/2 5 times u to the negative 5th over negative 5. And then you can see, oh yeah, I'm getting 5 times u to the negative 5th. I'm dividing by a negative 5 and a negative 2. But again, I don't want you to have to do that work. I want you to be able to just say like, okay, I know how to integrate 1 over some linear function of x to a power. It comes up often enough that you want to be able to do that without having to do it every time. All right, let's look at some more examples. What time is it? Okay. I know we should say at least 20 to 30 minutes for talking about improper intervals. So let's look at this one. The integral of x minus 2 over x squared minus 4x minus 12. Degree on top less, check. Bottom factors, does the bottom factor? Yeah, the bottom factors, right? X minus 6 times x plus 2, check. Oh, wait, should I do it? I should try use that just to be sure. So u is x squared minus 4x minus 12. Du is, du is 2x minus 4 dx, which is definitely 2 times x minus 2 dx, which I have. So here, my 1/2 du is x minus 2 dx. So I definitely should do this with a u substitution. This is going to equal the integral of 1/2 du divided by u, which is going to be 1/2 the natural log of the absolute value of u plus c, which is 1/2 the natural log of x squared minus 4x minus 12. Interesting. You could also do this using partial fractions, but it's more work. Does anyone want to see that? I really you would never do this with partial fractions, but I could totally show you guys if anyone wanted to see it. But the answer is no, that's totally fine. Sounds like the answer is no. All right. I will point out if you do this using partial fractions, your answer will probably look slightly different. You might get a different, like you might have an extra constant added on at the end. Although probably not. I don't think you actually do in this case. I think you probably get exactly. So I would bet, my bet is that your answer, if you do this using partial fractions, is going to be 1/2 natural log of the absolute value of x minus 6 plus 1/2 natural log of the absolute value of x plus 2, which doesn't look exactly the same at first until you realize that you can put these together. When you add logarithms together, you multiply their insides together, and x minus 6 times x plus 2 is exactly x squared minus 4x plus minus 12. So your answer might look a little different until you realize the logarithm rules let you think of the same. Okay. So let's look at something like this. The integral of x over x squared plus 4x plus 4. Definitely not going to work for a u sub here. That's a good question. So someone asked, will we ever run into a partial fraction or improper? So these are two different questions, and the answer to one is yes, the answer to the other is no. So the first question is, will we ever run into a partial fractions problem where we also have to integrate by parts? And the answer to that is almost always no. Someone could come up with something super duper extra funky where your partial fractions then became integration by parts. But almost it's really the issue is, right, partial fractions are just rational functions of x. It's not a mixture problem, so it's not really ever going to lend itself to being an integration by parts problem. You could try really hard to make it so you had to do integration by parts, and like it would be fun. It's probably very unlikely. On the other hand, improper integrals, definitely you have integration by parts showing up in them quite frequently. So maybe not quite frequently might be an exaggeration, somewhat often. Yeah, so like for example, we will certainly look at some integral improper that's like the integral from 0 to infinity of x e to the negative x. That's definitely a very common improper integral because it represents some sort of distribution function for something. And it definitely requires integration by parts. And also L'Hopital's rule, which I don't remember. Did we talk about L'Hopital's rule last quarter? You guys remember? Did we? I don't remember. Well, we'll talk about it. We'll talk about it either today or next week. No, yeah. So, well, some people we'll get there in a minute or a few minutes. Some people kind of hand wave their way around it. We'll talk about both kind of things. Well, let's look at this integral. So it definitely could be done using partial fractions. Right, this is the integral of x over x plus 2 squared. But I want to point out, and actually I do want to do this one both ways. Yeah, well, so someone wrote, the professor kept saying don't use L'Hopital's rule, and that's because you typically use L'Hopital's rule for limits in 16a, and they want you to learn how to do limits these other ways, because L'Hopital's rule is kind of something we learn later. But there are going to be some limits where so most of the limits you saw in 16a, you didn't need to use L'Hopital's rule for, although you could have if you know what it was. But there are some limits we're about to encounter where you kind of have to use L'Hopital's rule. So yeah, we'll talk about it. So there's two ways of doing this integral. One way you could totally do is with a u substitution. You could let u equal x plus 2. Your du is dx. And so when I write this, I get the integral of, well, I've got dx becomes du. X plus 2 becomes u. And help me out, everybody. What am I going to replace x with if u is equal to x plus 2? Right, it's going to be u minus 2. And then I can do the thing, since I've got a fraction where I've got a single thing in the denominator, I can divide each thing by that. So I'm going to write this as the integral of u over u squared minus 2 over u squared, which is the integral of 1 over u minus 2u to the negative second. Integral of 1 over u is the natural log of the absolute value of u. Integral of minus 2u to the negative second is minus 2u to the negative first divided by negative 1 plus c. Plugging back in what everything is the natural log of the absolute value of x plus 2. Minus 2 over minus 1 is positive 2. So it's 2 times u to the minus 1 or divided by u. So 2 divided by u is 2 divided by x over 2. Sorry, 2 divided by x plus 2 plus c. So that's one answer. The natural log of the absolute value of x plus 2 over x plus 2 plus c. But we also could have done this using partial fractions. We could totally say that x over x plus 2 squared equals a over x plus 2 plus b over x plus 2 squared. I did write them in ascending order. Sometimes I do the other way. So multiply everything by x plus 2 squared. You get x equal to a times x plus 2 plus b. All right. So then using a convenient value like negative 2, if x is negative 2, then negative 2 equals a times 0 plus b. So b has to equal negative 2. And then I've run out of convenient values, but I could just equate coefficients and say, well, I have 1x on the left, and I have ax on the right. So a has to equal 1. Which makes sense, right? Because that's the only way I'm going to get 1x is if a is 1. So this is equal to 1 over x plus 2 minus 2 over x plus 2 squared. And actually, I think you guys can see we're actually going to get the actually exact same answer. So if we integrate that, I guess I'm going to write it here. So if we do the integral of x over x plus 2 squared, which is the same as the integral of 1 over x plus 2 minus 2 over x plus 2 squared. Integral of 1 over x plus 2 is the natural log of the opposite value of x plus 2. Integral of minus 2 over x plus 2 squared, well, that's minus 2x plus 2 to the negative second. And using my power rule, I get minus 2 times x plus 2 to the negative first divided by negative 1. Those cancel and give you a plus 2. That's exactly what I have here. So this is the natural log of the opposite value of x plus 2 plus 2 over x plus 2 plus c. So sometimes you have choices. Sometimes you can do a u sub with a back sub. Sometimes you can do partial fractions. Usually, most people would probably opt to do it this first way we did it. But either way is fine. Yeah. Let's look at something else. Let's see. I should probably, let me do one more. One more partial fractions and then we'll move along. Let's look at something of, let me actually look real quick. Sorry, 1 second. I just want to see one thing. Where'd you go? See, do I have one? Oh, no, that's sure. No, I'm not seeing. I was looking for a certain type of problem, but I'm not really seeing. Okay, I'll just make something up. Let's look at something like, oh, excuse me. Let's look at, say, something like the integral of x cubed over x squared plus, yeah, let's make it interesting. Let's see, x squared plus 5x minus 4. Plus 4. Yeah. So the denominator definitely factors, I think, right? X plus 4 times x plus 1, yeah, factors. You want to make one that doesn't factor. So. But the degree on top isn't less. So before we can use anything, right? It might not actually be a partial fractions problem. Before we can even see that, we need to do polynomial division. So we're going to do x squared plus 5x plus 4 into x cubed plus 0x squared plus 0x plus 0. X squared times x will give me x cubed. X times 5x is 5x squared. X times 4 is 4x. Subtract. That's 0. 0 minus 5 is negative 5x squared. 0 minus 4 is negative 4x. Bring down to 0. Repeat the process. So we multiply by x squared to get negative 5x squared, negative 5. Negative 5 times x squared is negative 5x squared. Negative 5 times 5 is negative 25x. And negative 5 times 4 is minus 20. Subtracting that minus that is 0. The first thing to always subtract is 0. Negative 4x minus 25, so negative 4 plus 25 is 21x. And 0 minus 20 is plus 20. So this integral becomes the integral of your quotient x minus 5, which will be easy, plus your remainder 21x plus 20 divided by your divisor, x squared plus 5x plus 4. And it's this part that we're going to probably have to use partial fractions for, because it does not look like a u sub will work. U is equal to x squared plus 5x plus 4. Du is 2x plus 5. Nope, that's not a multiple of 2x plus 5. So partial fractions time. We're just going to leave this alone for a minute. So we're going to say, okay, 21x plus 20 over factor this as x plus 4 times x plus 1 equals a over x plus 4 plus b over x plus 1. Multiply both sides with your common denominator. So multiplying this by x plus 4 times x plus 1, you get 21x plus 20. Multiplying this by x plus 4 times x plus 1, you get a times x plus 1. You get b times x plus 1. Let's pick some convenient values. If we pick x equal to -1, on the left side, we get -21 plus 20, which is -1, equal to a times 0 plus b times 3. So you're going to get -1/3 equal to b. Letting x equal to -4. -4 times 21 is -84, plus 20 is -64. And -4 plus 1 is 3. So sorry, -3. So you're going to get a times -3. So you're going to get a equal to -64 over -3, which is positive 64/3. So we can then rewrite our integral as the integral of x minus 5 plus 64/3 over x plus 4 minus 1/3 over x plus 1. And then the integration is pretty straightforward. That's going to be x squared over 2 minus 5x plus 64/3, right? That's just your coefficient. And the integral of 1 over x plus 4 is the natural log of the opposite value of x plus 4. Minus 1/3, integral of 1 over x plus 1 is the natural log of the opposite value of x plus 1. Plus c. So that's how you do a problem like that. All right, let's talk about improper integration for the last 23 minutes here. So an improper integral is an integral where either one or both of your limits of integration are infinity. So here are a couple of examples. We'll do this one first, but I'm going to write down 3 examples. So here's kind of the most classic example of an improper integral. The integral from 1 to infinity of 1 over x dx. Or the integral from -infinity to infinity of x e to the -x squared. Those are both improper because infinity is one or both of your limits. Some sort of infinity is either one or both of your limits of integration. But here's another improper integral. The integral from 0 to 1 of 1 over x. Or the integral from, I don't know, 0 to 9 of 1 over the square root of 9 minus x. Or even the integral from 1 to 5 of 1 over, I don't know, the square root of, I have to be down, let's do the cube root. Sure, the cube root of x minus 4. So those are all improper because a limit of integration is some sort of infinity. These are all improper because the function you're integrating is undefined somewhere on your interval. Maybe more than one place on your interval of integration. 1 over x is definitely undefined at 0. 1 over the square root of 9 minus x is definitely undefined at 9. And 1 over the cube root of x minus 4 is definitely undefined at 4. But nowhere else, right? Because you can take the cube root of a negative. So it's perfectly fine to plug in 1 here. It's weird, right? 1 minus 4 is -3. The cube root of -3, I don't know what that number is, but it is a real number. There is an actual number that if you take the cube of it, it's equal to -3. And we call that number the cube root of -3. But the point is, each of these functions is undefined, usually in a division by 0 sort of way, at somewhere in your interval of integration. Here's another example, just to put one more in there. the integral from 0 to 1 of the natural log of x. And that's also improper because the natural log function is undefined at 0. So if your interval of integration makes your function undefined somewhere, it's also an improper integral. On the other hand, this function, this integral is not improper. Even though 1 over x is undefined at 0, it's not in our interval of integration. So this is not an improper integral. So 2 ways to be improper. If you ever see infinity, done, you're improper. Or if you look at your function, you're like, oh, that function is undefined somewhere either at one of the endpoints or somewhere in between one of the endpoints. That's also a way we say an integral is improper. And to deal with improper integrals, you have to use limits. So let's look at it. I can't imagine your teacher didn't do this first example, but I'm going to do it again because it's worth talking about. But it's kind of the classic, everyone does this example the first time. It doesn't hurt to see it twice. So I want to look at the integral from 1 to infinity of 1 over x dx. And here's the idea. We are going to instead say, so the thing is, you could totally kind of do it wrong instead of the right answer. Meaning, you could say, well, I know the integral of 1 over x is the natural log of the opposite value of x from 1 to infinity. And then that's the natural log of the opposite value of infinity minus the natural log of 1. And the natural log of infinity does blow up to infinity, right? If you think about the natural log function, the natural log function looks like this. And the natural log of 1 is 0. So you can say this is infinity minus 0, which is infinity. And when an integral is infinite, we say it is divergent. So doing it this wrong way will usually still lead to the right result. That said, your teacher probably isn't going to be cool with this. I could be wrong, right? Some people are like, I don't really care if you're really very precise, do whatever you like. I don't imagine that's going to be the case. At least not like maybe in the higher math class, everyone's like, we don't care, do whatever you like. We know what the works. So, but here I imagine they'd be like, no, you need to show the work. So this is not correct. Because the reason why this isn't correct is because we're treating infinity like a number, and it's not actually a number. So instead, here's the proper way. Well, actually, let's look at the picture. So 1 over x, we know what 1 over x looks like. Does this kind of deal. Okay. And what we're going to do is, instead of trying to do the whole thing, we're going to look at the integral from, say, 1 to b. Which is some amount of variance. So I would say, all right, I can say that the integral from 1 to b of 1 over x dx, well, that's totally fine because b is representing a real number here. So that's going to be the natural log of the opposite value of x integrated from 1 to b, which is going to be the natural log of the opposite value of b minus the natural log of the opposite value of 1. Natural log of 1 is still 0. So it ends up being just the natural log of the opposite value of b. Okay, but then you're asking, well, how do we then do the integral from 1 to infinity? Well, we're going to use a limit. So we say that the integral from 1 to infinity of 1 over x dx is equal to the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. That's the whole idea. We're going to say, instead of doing the integral from 1 to infinity, we're going to do the integral as the limit as b goes to infinity of the integral from 1 to b. Well, we know that this area, right, that area there is the natural log of b. Because b is positive, right? I dropped the absolute value, b is positive. So I can say, well, this is equal to the limit as b goes to infinity of the natural log of b. Because the integral, right, we just showed the integral from 1 to b of 1 over x dx is the natural log of the absolute value of b, and I'm dropping the absolute value because b is positive. But then we know that for the natural log function, as the inputs get larger, the outputs also get larger. So the limit of this as b goes to infinity of the natural log of b is in fact infinity, which means our integral diverges. And that's the correct way to show an integral, an improper integral either converges or diverges, is by saying, okay, you've got this problem limit of integration, whether it's an infinity or someplace where the thing is undefined, and you replace that problem with the letter a or b, typically, usually b for an upper limit, a for a lower limit. And then you take the limit of the integral as a goes or b goes to whatever is appropriate. So let me show you another classic example. So I want to find the integral from 1 to infinity of 1 over x squared dx. Okay. So again, the idea is very similar, right? You've got this function, 1 over x squared, does, I'd like to draw a little bit better. Looks kind of like that. And again, right, we're gonna say, well, let's just find the area under the curve from 1 to b. So we're going to rewrite this as the limit as b goes to infinity of the integral from 1 to b of 1 over x squared dx. Or you might even rewrite that as x to the minus second. Okay, well, we know how to integrate that. That's going to be the limit as b goes to infinity of the integral of x to the minus 2 is x to the minus 1 over minus 1 from 1 to b. Now, I would much rather write x to the minus 1 over minus 1 as 1 over negative 1 over x. This is the limit as b goes to infinity of negative 1 over x from 1 to b. Plug in the top limit first. You get the limit as b goes to infinity of negative 1 over b minus, plug in the bottom limit second, negative 1 over 1. So that's going to be the limit as b goes to infinity of negative 1 over b plus 1, or 1 minus 1 over b. Now I want to point out before we take this limit, which I'm sure we can all see what's going to happen, right? The area under the curve, right? That area there is 1 minus 1 over b. And then as we let b go to infinity, right, the part we're subtracting off gets smaller and smaller and smaller. The limit as this goes to infinity is 1 minus 1 over b goes to 0. So what's happening here is that the area is convergent, or the integral is convergent. So this integral from 1 to infinity of 1 over x squared dx is convergent, and we specifically say it converges to 1. People also just say it's equal to 1, but it's slightly more correct to say that it converges to 1. So if an integral is convergent, we know what it converges to, which we don't always. There are some integrals that we can show they converge without actually finding what they converge to. Most of the time, if you find an integral is convergent, you will have found the number that it converges to, and you should say that. You shouldn't just say it converges, but oh, it converges to 1 in this case. All right, let's look at, we got time for at least one more example, but I want to show you, I do want to show you one where we might have to use L'Hopital's rule. So let's do this one. Yeah, let's do this one. Let's do the integral from negative infinity to 0 of x e to the x dx. So now we're looking at something something that looks probably like this. Let's see. If x is negative, then x is negative, and e to the x, e to a negative is still positive. So it's going to be some negative thing. Probably looks vaguely like this, I think. I don't exactly know. Doesn't really matter, but kind of matters. So for this integral, we have to do integration by parts. So I'm going to write this as the limit as a goes to minus infinity of the integral from a to 0 of x e to the x dx. But I don't want to do integration by parts and have to write this limit with these limits of integration the whole step, the whole way through. So instead, what I'm going to do is I'm just going to do the indefinite integral off to the side. So I'm going to do the integral of x e to the x dx. It's integration by parts. I'm going to let u equal x. dv is e to the x dx. Yes, you could use tabular here, but it's only a one-step tabular. It seems kind of unnecessary to do a one-step tabular. Du is dx, and v is e to the x. So this is going to equal uv minus the integral of v du. Integral of e to the x is e to the x, so you just get x e to the x minus e to the x. I don't need to write the plus e because this is my own side work. So here's what I've got. I've got the limit as a goes to minus infinity of x e to the, I forgot there's a way to do this one that kind of works out fine. X e to the x minus e to the x from a to 0. So let's plug in our limits of integration. This is going to be the limit as a goes to minus infinity of 0 times e to the 0 minus e to the 0. Okay, that's minus 1. Minus a e to the a minus e to the a. Okay, most of this is fine. That's 0, that's minus 1. E to the negative infinity does go to 0. But negative infinity times e to the negative infinity is a little less clear. Kind of out of order. Let me go ahead and write it. Because here's what we've got. We have the limit as a goes to minus infinity of negative 1. And I'm going to rewrite these parts. I'm going to write this as minus a over e to the negative a. And minus minus is plus 1 over e to the negative a. So I want to be super extra clear about this. 1 over e to the negative a. A is going to negative infinity. Negative infinity, that's going to a positive infinity. E to a really big number is a really big number, and 1 over a really big number is going to 0. So this part's going to 0. On the other hand, this part here is a little less clear. Let me show you what I mean. I'm going to rewrite this as the limit as a goes to minus infinity of, I'm going to write it as negative a over e to the negative a minus 1. I guess I should still technically write this part over here. All right, so we know this is still going to go to 0. I've got on top, negative a is going to infinity. And on the bottom, e to the negative a is going to e to the infinity, which is also going to infinity. So I've got infinity over infinity. What do we do with that? Well, in this problem, there's actually 3 ways around this. Way 1, which I imagine some of your teachers might say. E to the infinity gets bigger much faster than just infinity. Or e to the something gets bigger much faster than just something. So what you have here is you have a small infinity over a big infinity. The denominator is growing much more quickly than the numerator. So that's going to go to 0. That's one way of saying it. Another way of saying it, which doesn't always work, but does happen to work for this problem, is that you can actually take this expression and you can factor out an e to the a. So I could totally rewrite this as the limit as a goes to negative infinity of still got a -1. And here I can factor out an e to the a and write it as minus e to the a. Oh, actually, this doesn't make it better. No, I lied. This is not actually any better. So scratch that. We're not going to do that. Doesn't really get any better that way. No, it doesn't. So instead, what we're going to do, so this is probably what some people will be like, you can just say this. An exponential function going to infinity always grows much faster than any linear function or any polynomial function. So this was a squared over e to the a or a cubed over e to the a. E to the a would still be getting bigger faster. But the other way is to use what's called L'Hopital's rule. L'Hopital's rule says if you have a limit as x approaches some t of f of x over g of x, if this is an infinity over infinity type or a 0 over 0 type, then you can say that this is equal to the limit as x approaches t of the derivative of the top over the derivative of the bottom. So the limit of a quotient is equal to the limit of the quotient of the derivatives. It's not the quotient rule. You're seeing the derivative of the top and derivative of the bottom. So what you could say here is that the limit as a goes to minus infinity of negative a over e to the negative a is equal, which is an infinity over infinity type, is equal to the limit as a goes to minus infinity of the derivative of the top, which is -1, over the derivative of the bottom, which is e to the minus a times -1. The -1's cancel. And then you've got 1 over something that's still infinitely large, which is going to go to 0. So that's the very, very brief gist of L'Hopital's rule. If you have a limit, so L'Hopital's rule is only for limits. If a limit that's an infinity over infinity type, like we have here, you take the derivative of the top, the derivative of the bottom, and then take the limit of that. And if you get an answer, that's your answer. So this part's 0, this part's 0, so it's -1, so the whole thing is -1. So this integral converges, and it converges to -1. Just so in the last 2 minutes, let me say 2 more words about L'Hopital's rule. So again, I don't know if your professors are going to require you to know this or not, but it's a useful tool that you all should be aware of. So let's say I want to take, I'm going to do 2 examples here that you already should know the answers to. Everybody should be able to tell me in the chat what's the limit as x goes to infinity of 5x squared plus 3x plus 1 over 7x squared minus 2x plus 2. Everybody in the chat, what is this limit? I know you know it. Or nobody in the chat. That's also an option. It might have been a while, but this limit's equal to 5/7. We have a rational function. The degree on top and the degree on bottom are the same, right? They both are degree 2. And the limit of this is the quotient of the leading coefficients. One way to show the work, which we definitely did back in 16a, is to divide everything by x squared. This is equal to the limit as x goes to infinity of 5x squared over x squared plus 3x over x squared plus 1 over x squared over 7x squared over x squared minus 2x over x squared plus 2 over x squared, which is equal to the limit as x goes to infinity of 5 plus 3 over x plus 1 over x squared over 7 minus 2 over x plus 2 over x squared. But anything divided by x or a power of x, if x is going to infinity, that's going to go super small. So is that, so is that, so is that. So you get 5/7. But the point is that although you don't need to use it, L'Hopital's rule would totally work here. So you take a look at this, right? If you look at this limit, well, I definitely have an infinity over infinity type. the top as x goes to infinity is getting infinitely large. The bottom as x goes to infinity is also getting infinitely large. And it doesn't actually matter if it's a positive or negative infinity, although in this case, they are both positive infinities. So we can take the derivative of the top and the derivative of the bottom. 10x plus 3 over 14x minus 2. The top is still going to infinity. The bottom is still going to infinity. I'm going to use L'Hopital's rule again. Often when people use L'Hopital's rule, they write a little L apostrophe H over the equal sign to indicate that they have used L'Hopital's rule. What's the derivative of 10x plus 3? Oh, it's 10. What's the derivative of 14x minus 2? Oh, it's 14. The limit of a constant is just the constant. So this is 10 over 14, which is equal to 5 over 7. So I just want to do an example that you already know is actually equal to 5/7 and show you that L'Hopital's rule also gets you equal to the same number. So if you have an infinity over infinity type of limit, or a 0 over 0 type of limit, which I know we didn't talk about, you can use L'Hopital's rule, where you take the derivative of the top, the derivative of the bottom, and then take the limit of that. And if it's still an infinity over infinity, then you can do it again. Take the derivative of the top, derivative of the bottom. Great.